In this video, we're going to be talking a little bit more in depth about conformations of cyclohexane. Cyclohexane is of particular interest in organic chemistry because there's a lot of chemistry that can be done with it. It also is a good tool for talking about stereochemistry. So as we saw, if we're looking at just cyclohexane, C6H12, we saw that between the two chair conformers, there is no preference. They are degenerates. They have the same energy. Because there's no preference, they are rapidly in equilibrium with one another, flipping back and forth with really no preference unless you bring it down to very, very low temperatures where you can isolate the two chair conformations. But what happens if we start introducing substituents? So let's, instead of looking at just cyclohexane, let's look at methyl, the methyl substituent, methyl cyclohexane. Let's examine what the chair conformations look like for that. So the first one, I'll just draw a chair. So say I take that methyl group and I put it pointing up. It's on one. I haven't indicated whether it's up or down, so I'm just going to assume that it's pointing up. Now, since this is, and we'll see this in chapter 4, this is not a stereocenter. It doesn't matter really whether I put this up or down to start because it'll be the same. So I've started by putting it axial. I put the CH3 group axial. I'm then going to do the chair flip. And I'm going to, if we remember, if we do a chair flip, all axial become equatorial, and all equatorial become axial. So since we had an up axial, so this was up axial, this will be an up equatorial after we're done. So we've gone from axial to equatorial. And the question is here, which one of these is the preferred structure? At first glance, it may be unclear, but if we look at this axial situation, we notice that we also have two hydrogens that are pointing up nearby. And if I instead draw this CH3 not as a CH3 group, but I instead draw out the other H's, so I have an H, I have an H, and I have an H, kind of in a tetrahedral structure, we'll see that we kind of have these clashing interactions, this steric bulk that we've seen before between these hydrogens. They kind of crash up into one another. If we count, we see we have 1, 2, 3 to one and 1, 2, 3 to the other. This kind of steric clashing we call 1,3 diaxial interactions. And 1,3 diaxial interactions are unfavorable because we're putting steric bulk near one another. Similarly to if we had torsional interaction, this van der Waals interaction is going to be unfavorable. So having this CH3 group axial causes these diaxial interactions to occur. However, when we put this CH3 group equatorial, now we've put an H axial, and the H's that would be 1,3 diaxial to that H. H's hydrogens don't experience that same 1,3 diaxial interaction because they're so small. Only larger groups, alkyl chains or larger substituents are going to experience these 1,3 diaxial interactions. So if we were to compare the axial and the equatorial conformations, these two chair flips, we're going to see that this equatorial conformation is going to be much more preferred than the axial conformation of the CH3 group, and that's because we're minimizing the 1,3 diaxial interactions in the conformation by forcing the methyl group to be equatorial versus having it be axial. So what happens if we have more than one substituent? What happens if we have two substituents? And this is a point where we can start talking about stereochemistry. And we'll see a lot more of this in chapter 4, but we can start talking about stereochemistry now. So let's look at an example. Let's look at cyclopropane. Let's look at two different we call them stereoisomers of cyclopropane. I'm going to draw in all of my bonds. I have one pointing up, one pointing up, one pointing down. Okay. So let's say in this case I have a methyl pointing up and a methyl pointing up. And in this case I have a methyl pointing up and a methyl pointing down. And this would be filled in with hydrogens, of course. They could be filled in with other things, but in this case we'll fill them in hydrogens. How do we differentiate between these two structures? It turns out that we have what's called, we have a system of notation called relative stereochemistry that we can use to compare two groups. Now, this only works if we're comparing two groups. If we had three substituents on this cyclopropyl ring, we would not be able to use these denoters. But since we have two groups, we have two methyl groups that we're comparing, we can. So in this first case, we have a methyl pointing up and we have a methyl pointing up. Since these are on the same side, we would call this, the relative stereochemical term we would give to these two methyl groups would be cis. So we would call these methyl groups cis to one another. In this case, where we have a methyl group pointing up and a methyl group pointing down, they're on opposite sides of the CC bond, we would call this a trans isomer. So cis means they're on the same side, trans means they're on the different sides. Now, when we're thinking about stereochemical arrangement and relative stereochemical terms, there can be a difference in energy between the cis and the trans isomers. In fact, if we draw these in 3D, I'm going to draw the cis isomer, so I have the CH3 pointing up. And I'm just going to indicate the CH3s, and I have the CH3 pointing up, versus over here I have the CH3 pointing up and the CH3 pointing down. I guess I'll fill in the other H's. Sorry, this is an H pointing up. And then two H's pointing down. If we examine, so this would be the cis isomer and this would be the trans isomer. The cis isomer, if we were looking down this bond, if we were to draw a Newman diagram of these, we would see that the CH3 groups are under a great degree of torsional strain because they are eclipsing one another. Now in the trans isomer, the CH3 group is eclipsing a hydrogen, so the torsional strain has been greatly reduced. So in this case, the trans isomer would be much more stable than the cis isomer because we are reducing the amount of torsional strain that occurs in the molecule. We can indeed apply this to a vast host of different types of molecules, and let's take this and use this to compare different types of cyclohexane rings. So let's consider, let's go from one substituent on cyclohexane to two substituents on cyclohexane. So I'm going to draw two different isomers. So I'm going to have the cis isomer where they're both pointing up. So this would be cis 1,2 dimethyl cyclohexane. And then we would have the trans isomer. So this is cis and this is trans. The cis meaning they're both on the same side, the trans meaning they're on opposite sides. And my question is, which is more stable? And cyclohexane, unlike the cyclopropane, we have to examine both chair flips of the molecule to determine which one is going to be actually more stable. So let's examine these two molecules. Let's start with the cis. So we're going to start by drawing the chair form of the cis cyclohexane. Okay. These are both up. So I'm going to draw one up. I'm going to call it axial. And you could start anywhere around this ring. I just like starting at this corner. This is going to be up. And then this is going to be up as well. And we can make sure that we're doing this correctly by drawing in the other bond. If we look at this apical position, we see that the CH3 is up relative to the hydrogen, and it is axial. If we view this position, we see the CH3 is equatorial, but is up relative to the hydrogen. So both of these CH3s would be considered up, pointing up, and they would be cis to one another. So we have one axial, that's this one here, and we have one equatorial, which is going to be this one here. So let's do the ring flip. Let's see if we can make it more stable by doing a ring flip. So if we flip the ring, we're going to invert the everything that's axial is going to become equatorial. Everything that's equatorial is going to become axial. So we're still going to have two up. We're going to have an up equatorial. I'm going to put it right here. This is up. And then we're going to have an up. That equatorial becomes axial. And that's going to be up. And if we examine whether they're axial equatorial, we have one equatorial. That's this one here. And we have one axial. That's this one here. So if we look, we go from one axial, one equatorial to one equatorial, one axial. So there's really no preference between these two chair flips, and they both have one axial, one equatorial. So it's okay. It has one equatorial, but it does have one axial, and we will get the 1,3 diaxial interactions between the axial position in both of these cases. So the cis one is okay, but let's examine the trans one. So let's draw the ring structure for the trans isomer. I'm going to have one up and one down. So I'm going to start at the same position. Doesn't really matter again. I'm going to put one CH3 up, and then I'm going to put one CH3 down. And again, we can check to make sure we did that correctly by drawing in the fourth bond. In this case, we have the CH3 up relative to the H. In this case, we have the CH3 down relative to the H. So these would be trans to one another. In examining these two positions, we see that we have two axial. Two axial is very unfavorable. You're going to get 1,3 diaxial interactions on both sides of the ring in this case. So this isn't great, but we still have to examine the ring flip. So let's examine the ring flip. So remember, ring flips take all the axial and make them equatorial, and all the equatorial and make them axial. So if I started with two axial, I'm going to end with two equatorial. So I need one equatorial up, this up, and one equatorial down. And again, we can double check to make sure we did this right by drawing in the fourth bond. I see that this is an up CH3 and this is a down CH3, so they are still trans to one another. And what we see is we now have two equatorial positions. So going back to the question, which one is more stable? If I look at the cis isomer, I see I have one axial and one equatorial across the board. So that is kind of middling in stability. If I look at the trans isomer, I have one chair conformation where it's two axial, and one chair conformation where it's two equatorial. So this tells us two things. One, this tells us that this isomer, this conformation is going to be much more favorable than the two axial isomer, or the two axial conformer, because two equatorial is much, much more stable than having two axial. What this also tells us is the trans isomer overall is going to be more stable because we can access two equatorial positions, whereas in the cis isomer, we can only access one equatorial position. So to answer the question, which one is more stable, that would be the trans isomer, or the trans isomer versus the cis isomer. And that's because we can access two equatorial positions versus only one equatorial position in the cis isomer. So just one last note in this section. If we need to choose between which groups are equatorial and which groups are axial, big groups or bigger groups, you want to put equatorial to minimize the degree of 1,3 diaxial interactions that we have. So, for instance, let's look at cis methyl with a we call this again. This is the T-butyl group. T-butyl is a particularly large group. So when we're looking at this, we want to try and make this group equatorial. Now we want to try and make both groups equatorial, but if we can only choose one to make equatorial, we want to make this bigger group equatorial preferentially. So let's see which chair conformation is going to be the most stable. So in this case, I have a T-butyl up and a methyl up. I'm going to put the T-butyl here. I'll draw this one out. And the methyl up. And we can check to make sure they are cis to one another by drawing in the hydrogens, and we see that they're both up. Now this one, if we look, this T-butyl group, and just to illustrate a point, this is a C, 3 H's pointing out, and there's 3 of them. T-butyl is a huge group, so this amount of steric bulk is really, really making this type of conformer very unstable. So having a T-butyl group axial is not preferable. But let's look at the chair flip. So if we do the chair flip, remember axial will become equatorial, equatorial will become axial. So our axial T-butyl is now equatorial T-butyl, and I'll just abbreviate it as T-butyl. And now we have an axial methyl. Now, as we saw, axial methyl is not great. You are going to get the 1,3 diaxial interactions here and here. But if we are comparing it with a T-butyl axial, a methyl axial is going to be much, much preferred. So what we see is that this conformer is going to dominate the equilibrium here. So it's going to be strongly favored in this direction versus the other direction. We're going to strongly favor the methyl group being axial over the T-butyl group being axial to minimize the steric hindrance caused by 1,3 diaxial interactions.